going to look at decimals, and some of you I know like working in decimals better because that's what you did when you were fractions from models and change some to decimals to think about them. The first thing I kind of want to talk about is the language we use when we talk about decimals. So the first thing is that word deci right there comes from Latin word meaning 10. So we talk about our decimal system, and the reason we have a decimal system is because it is a base 10 numbering system. We don't actually have a digit that is the digit for the number 10, but we have 10 digits. The digits we have go from 0 up to 9, right? So our language, what I'm talking about here, is the language we use for our placeholders in the decimal number system. So we have some placeholders. I think that's the things I'm going to go with today. And what do we call this first place? So here's my decimal right here. If I have a number 2 spots before the decimal and a decimal point, that point is the decimal, what is this place called? That's the tens. What's this one called? Ones, or sometimes you'll hear it called the units place. But we tend to teach it as being the ones place for sure. What do we call this location here? Tenths. And the difference is the ending part, right? It's got a TH on the end. This is the tenths. The next one is what? Hundredths. I'm going to make sure you got the TH there sound on the end. What's my next one? Thousandths. Oops. And then what? 10 thousandths, that's right. And we put a hyphen between the 10, the word 10, and the word thousandths. I've got one more location. What's my last location then? Not yet. 100 thousandths. If we were going to go one more, then it would be millions. Yeah. So this one's 100 thousandths. And again, I've got 100 hyphen thousandths. Thousandths, sorry. Yeah. The THS at the end. So these are our different placeholders, and we're going to actually work on our language being more correct. So when you take a look at the next slide, you have a number written, and this is the numerical form of the number, and I want us to actually say this correctly, and we're going to write it down in the words that would correspond to that. So let's take the number before the decimal point. What do we say? 32. And when we write 32, we use a hyphen on that, right? So we have 30 dash 2. What do we say for that dot? And. Yes, we do. No, I shouldn't have put a comma here. And. Now, I want you to ignore where this number is. But I just want you to say what the number, if you saw the number 4236, not where it's located or anything else, what would you say to 4236? What number is that? And that's exactly what we say first right now. Okay? We say 4,236. So 4 dash thousand. I'm sorry, there's no dash. Right. 4,000. 200 36. Now we say the location it's in. The location is in based on where the last number is. So what is the place value of my 6? What is 4 places over going to be? That is the 10,000th location. And so we indicate that right at this point by saying 10 thousandths. So this number is 32 and 4,236 10,000ths. It's actually not 32.4236. Which is what we say all the time, isn't it? If I just asked you to say it, that's what you guys would have thought. Say point or dot or something between them. This number is 32 and 4,236 10,000ths. So we're going to do the opposite of this now and go the other direction. We have a number written out in words, 536 and 76 thousandths as a numeral. So the first thing that we should be looking for sort of in this language is what word? What's kind of a keyword that tells us a lot of information? The and. It really does. Because what does that and tell us? That's the decimal. So the value, written form or otherwise, that comes before the and is going to come before the decimal. So what's going to come before the decimal? 536. So 536, and then I have a decimal point. Now this says 76 thousandths. So can you tell me the numerals that I need to write next? What comes next? A 0? And then the 7 and the 6. So why did I put a 0 here first? How did I know that I needed that? Oh, I like the word stretch. That's a good word. It needs to stretch all the way over to what you were saying, which is the thousandth spot, right? The thousandth spot is 3 decimal points. So the fact that I have thousands here tells me that I'm going to have 3 decimal points, right? And I've got to stretch the number 76 to end in that location. That's a good word. So we end up with 536.076 if we're writing the decimal expression as a number. All right, base 10 expanded form. We talk about a lot when we first learn addition. Usually addition is where I see it used in other classes I'm teaching. But we talk a lot about the addition components of base 10 values when we have numbers that don't have decimal points. In other words, if I wrote the number 536, I would say that's 5 hundredths. So I could write down 5 100ths, or 500. And then I would say 30, so it's either 30 or 3 times 10. And then I've got the number 6 at the end. We can do the same thing with base 10 with decimals. So I want to focus more about the actually decimal part of this. So when we said this a moment ago, what was this location called right after the decimal point? Tenths. Do you know why it's called the tenths? Yes. It is a tenth, and the language actually comes from the language we use for fractions, because this point right here is 1/10 as a fraction. Yeah. So to me, it would mean 1/10. So think about dimes, right? A dime is 1/10 of a dollar. So one way of writing it as a fraction form is 1/10, hence tenths, 1/10. And then of course this one should be hundredths. And this one was thousandths, so it's 1/1000. This is 10,000, so it's 1/10,000. And this one is 100,000ths. So we're going to take this number 103.03, and I didn't do the first part, which I think you've probably seen that plenty of times before, but we'll do it, of course, for the problem. We're going to write this in expanded form. So the first thing we see is this number 1. This number 1 represents 1 times what base 10 number? Not with powers, just what number is it? It's 100, right? This is 1/100. So if I gave somebody money, I would be giving them, and I was trying to do it in the smallest denominations possible, I would be giving them one $100 bill, right? That's how you want to think of it. That's 1/100. I have a 0, which you can write in, and I'll go ahead and write it in for now, just so that we recognize that I would give them 0 $10 bills. 0 tens. And then there's 3 ones, agreed? So I can write that as 3 ones. The rest of this gets written using this sort of notation I did above. So I've got a 0, and then this location is the tenths. That is 1/10. And then I have 3 in the hundredth spot, so this is 3 hundredths. Which would be 3 pennies, right? Pennies, hundredth of a dollar. I want you to be aware of this note at the bottom because your book does something, you know what, I didn't even look to see if this book's still doing it, but I'm pretty sure that they will. When they change the edition, I don't think they're going to change this. Your book tends to use negative exponents for these, so what you might see your book do is this. They might write this. Those things. I want you to be aware that the book may do this to you. Okay? And there isn't anything wrong with using a red and red. It's perfectly 100% mathematically correct. But it's also not very intuitive for what's really happening. Correct? And I look at that and I don't see money anymore. The way that I wrote it earlier, I saw money. And I saw really clear coins and dollar bills and kind of way we write around money. When I see it in this form, I don't see that any longer. It is base 10, it is expanded form, but when I see this form of expanded form, to me this actually makes more sense of the number, whereas this one sort of hides what's going on. So I would actually prefer that you use this notation right here. Okay, I've got all sorts of crazy things going on the screen. So I would really prefer that you just leave it written as the first form, but just recognize that your book might write it differently, and that's okay. All right? Nobody's complaining, so I guess that's okay. We're going to draw a decimal square grid. A decimal square grid is a 10 by 10 grid, and it contains 100 small squares. And as I draw it, it's not going to be perfect unless I use my tools up here. And so I'm going to use a little bit of my tools, but the first thing I want you to do is, and mine doesn't even look good because it doesn't, but you're going to draw a square. So draw yourself a square. And in your square, what I want you to do is I want you to divide it into 10 columns and 10 rows. All right? I'm going to do what I can up here to make that happen too. And so here's my decimal square grid. I've got a 100 by 100 grid. Right, I'm a 10 by 10 grid, have 100 dots. And we're going to shade in, that is, we're going to draw a square grid for the number 23 hundredths. The dot 2, 3 is 23 hundredths. Well, this grid has hundreds. Each of the little grids is a 1/100th of the value. Okay, the whole big box is the number 1. The grid, I can fill in 23 of them. So you could technically fill in 23 anywhere in the grid that you want. I'm going to discourage you from doing so. Please fill them in a way that would make sense, so that you can count them easily. That is, fill in either a whole row or a whole column, so you get 10 at a time. I chose rows. You can choose whatever you want. And then you need 3 more. And then I know I've got 23. I just look at this problem, and I have the feeling that if you asked one of your, I don't know, second grade boys to do something like this, some kids, I think it's really funny and cute to fill in 23 squares all unattached. Make you count them as their teacher. Think about that when you give directions on something. Help them draw it so that it's easy for you. All right. A rational number, A over B in simplest form, can be written as a terminating decimal. So not all rational numbers, which is the last section that we dealt with, right, can be turned into decimals that terminate, that is a decimal that stops. One fraction in particular that you see used a lot is the number 1/3. 1/3 does not have a closed decimal form. It is 0.3 repeating, okay? And there are lots of fractions that are like that. They've got some sort of a repeat in it or something, okay? So this actually tells you how you can know if it's going to change into a closed, confined form. So the way that you have to do this is, first of all, it says the prime factorization of the denominator contains 2's and 5's. But before we get to that, it says this right here. It says the fraction has to be written how? In simplest form. Which means before you do anything else, you should make sure that the fraction is reduced. This is really important. Because if it's not reduced and it doesn't follow the rest of the pattern, you don't know anything. You have to reduce the fraction first. Once the fraction's in reduced form, if you take the denominator and you factor it into its prime factor. So what are primes? Tell me some prime numbers you know. 2, 1, actually 1's not. It's a tricky one, but 2 is, 5 is, 7 is, 13, we skipped 3, 11 works, 17. So what's the key concept behind prime numbers? What does it take for a number to be prime? It doesn't reduce. So, I like what you said. You said you can understand this. Right. It only has factors of 1 and itself, which means we can't reduce it, which is what Shana was saying. Okay? Now, the reason that I'll tell you because the 1 is the tricky one. The reason 1 is not considered a prime number is because the definition for prime number says it has 2 distinct factors, and the number 1 would only have 1 factor, right? Itself. Or 1, however you do it, it's only 1 factor. Prime numbers have 2 distinct factors, the number 1 and themselves. Okay? So we take the denominator and we make the denominator into all the primes, factors that it has. And we'll do that for part B, so you can see it work. Once you do that prime factorization, if the prime factorization of the denominator has only 2's and 5's, then you can write it as a terminating decimal. If it doesn't have 2's and 5's, then you can't. Okay, it only has 3 in there. Okay, we have a 3 wasn't good. Yeah, 3 in there. Or if it had a 7 in there. Or 11 in there. If it has another prime number as part of its factorization, unless it's 2 or 5's, then you would be able to do it. All right, so problem number 5 says mentally determine if the value has a repeating decimal, is a repeating, represent as a terminating decimal, excuse me. Write it as a terminating decimal if so. So I know it says mentally, and I get that, but I can't read your mind. So we're going to do a little bit of showing what our brain is thinking when we see the word mentally. Okay? So the word here says mentally, and I'm trying to decide if this actually can be written as a terminating decimal. And the way that I do that is to first decide, is it in simplest form? Can it be reduced? So can this be reduced? No, I'm done. It can't be reduced. So the second thing that I would do then is I would take the denominator and I factor it. I want to show you, there's 2 ways of factoring, so I'm going to show you one that you may not have seen before. What number is the smallest number that you know that divides 8? 2. And I'm going to write it kind of like we do with division. I'm going to put a 2 on the outside. What is 8 divided by 2? 4. The next thing I'm going to do is I'm going to build upon this, kind of like a ladder. Okay? Now I'm looking at only the number 4. You ignore the 8 and 2. What is the smallest number that divides 4? 2 again. And what does divided by, division by 2 give you? 2. Those are the prime numbers, and you're done. Right? I'm down to all prime numbers. 2 times 2 is 8, which you probably knew. This is just a nice kind of closed way of writing it. So my 8, which is my denominator, is 2 times 2 times 2. So let's go back again. It says, if the prime factorization contains only 2's and 5's, then it's a terminating decimal. Is this a terminating decimal? Yes. Okay. It contains only 2's and 5's. It doesn't have any 5's in this particular one. That's okay. But it doesn't contain anything else. That's the kicker. There's no random other numbers in here. Now, the second direction says that if it does, we have to find the terminating decimal. Okay? So my first answer is yes. Okay, so it doesn't have to have 2's and 5's. It's probably not the best phrase to say there, right? But that's not what it says. So, but it can't have any other numbers in its factorization. Right. So the denominator has to be factored into 2's or 5's or 2's and 5's. If there's any other factors down there, like 3's or 7's or 11's, then it's done. You can't do a terminating form for it. once you do a terminating form for this, how do we do a termination form? Well, so let's take a look at this. This says I've got 3 divided by 8, so I'm going to write it as 3 divided by 8. And this is another one of those examples. It's going to be long division, and you're going to write it out. I fully recognize that your calculator can find this very quickly. Okay? You may even just know off the top of your head on some of these what they are. That's not the point. Okay? So when you teach a child to long divide in 4th grade-ish, they don't use the calculator to do it. Right? So what you do is what? What do you do from this point on long division? Right, you put a decimal and you put a 0, and then you think about it like it's the number 30, right? I know there's a 3.0 there, but we think about it like it's the number 30, and we ask ourselves this question: how many times does 8 go into 30? And what is it? 3 times. So we bring the decimal point up to right here, and we put the 3 after the decimal point. And we say 3 times 8 is 24, and then we write the 24 down. And after we do, we subtract. So what is 30 minus 24? 6. And then what do we do? What's that? We do put another 0, you betcha. Because there's no remainders in what we're doing, right? We're looking for the decimals to end up giving no remainder. Once we get to a 0 remainder at the bottom, that's when we're done. But I'm not there yet because I've got 6. So then I've got a 6 and a 0. So how many times does 8 go into 60? 7 times. What is 7 times 8? 56. And I subtract. So what's 60 minus 56? 4. And I'm going to do it one more time. I'm nearly there. So you could have to do this several times. It could be a really long terminating decimal possibility. But 8 goes in 40 evenly. How many times? 5 times 8 is 40. So this is my remainder 0, which tells me I'm done. So the solution is yes, and the decimal is 0.375, with work shown on how the 375 was arrived at. 375,000. Okay, so we're going to do part B the same way, same directions. First, the question is it a terminating decimal? So I like to do this, and I know you're not familiar with it, or at least probably not, so I'm going to do it again so you can see how it works. No? Some people like to do factor trees, which works as well. I think it's in the next, I don't remember which section it is. We'll talk about the benefits and detriments of the two different ways at some point here, about why one works better maybe for situations than others. Yeah, but if you like, we can. So 12, what's the smallest number that divides 12? 2, the smallest whole number. It's not 1. I should say the smallest prime number, that's what I should say. The smallest prime number is 2. And so what is 12 divided by 2? 6. 6 isn't prime, so I keep going. What number can I divide 6 by? The smallest prime. I can do a 2 again, and I get 3. I like doing them this way just because they're all on the same side. So there's my 3 values. So I actually know that 12 is 2 times 2 times 3. And the question is this going to represent a terminating decimal? And Madison says no, and why, Madison? Because 3. That's causing all kinds of problems for me, right? This right here is going to tell me that the answer is no. It will not be a terminating decimal. So what it actually means is it will be a repeating decimal. We'll get to that point later, but right now we're just looking for terminating values here. Yes, when the answer is no, it's good, right? It means there's less work to do. So don't be shy if the answer is no. That's great. Okay, comparing and ordering decimals. When you're comparing the size of decimals, we're trying to put them in order from least to greatest or greatest to least or whatever. The idea is to line them up. And you line them up by place value. And you read them from left to right. And then you compare them for different digits. So you may be able to look at it just like it is, but when we get to some of the repeating issues, you're not going to be able to do that as easily. So what I really want you to do is to line them up, like what I'm saying up here. So we're going to line them up one underneath the other. So the first one is 13. There's a decimal point, and then 4919. The second is a 13, decimal point 492.
Be careful that you're actually lining them up so that each of the places are lined up on top of each other to be able to compare. The third one is 13.49183. And my last one is 13.49199. And it says least to greatest. So looking at these, what we should first notice is that the first two decimal places are the same in all of them, right? I don't have mine lined up all that well. So I'm actually looking at the third decimal point before I get to compare. Let me move this over, I can't do it that way. That's better. Whoa. Okay, so after my green line, I think you can tell me which one's the biggest, right? The biggest one is which one? 0.492. So I'm supposed to be writing this least to greatest, so I'm going to actually write the greatest one first at the bottom. So this is 13.492. And I can, ignore that. I don't really need that one anymore. Okay. All right, so I have three more. I have 19, after the green line down, I've got 19, 183, and 199. Which one is the smallest? The first top one has the fewest digits, but it's not the smallest. The one that ends in the 8, 3. Because this is 19 and this one's 18. So this one, that's the third one listed, is actually the smallest. There's my smallest one. Ready to do that? Yeah. Okay. So we can kind of ignore that one now too, yeah? Okay, so between the first one and the last one, which one's the smallest? The top one. And why is it smaller? Yes, and this is a good thing to notice. It might help you to actually make them the same length. I don't want you to think it's smaller simply because that's fewer, numbers there. It really doesn't, right? I'm really comparing 190 and 199. And 190 is smaller than 199, so that's going to be listed next. So this is 13.49190, and then I've got 13, or you can put the 0 or leave it off, it doesn't matter, 9199. So this would be the correct ordering from smallest to greatest. And again, you may be able to look at them where they are and see that, but when we get to the repeating decimals, it's much more difficult to do that, okay? So if you line them up, then there's no question. All right, so here is a question for you that I think Lindsay brought up a question, or at least I thought she was bringing up a question about this today. It's the word tenth. So the meaning of the word tithe. So the meaning of the word tithe, so when we talk about giving a tithe to the church, what do we mean? 10% or 1/10 of our income, right? So this is actually meant 1/10. So how is that related to decimals? What does it look like? What is the number 0.1, right? So this is, I'll put 0.1. You can put 0.1 if you like. 0.1 as a decimal. And just for kicks, let's do it as fractions or percents because you've already mentioned the percents, Shana. So it's 10% as a percentage. What is it as a fraction? 1/10 as a fraction. And I will tell you from just being in church and things that I've heard that some people really misunderstand this idea. They will say something like, I'm getting, my tithe, I'm just getting 5%. You can call it what you want, but that's not a tithe, right? That's just a giving amount you're giving. If you're giving a tithe, that means you're giving a 10%. There is no other percent. If you give a 20%, that means you've given a tithe plus an offering, right? Or some people will call that a double tithe or something like that. But tithe means 10%. Okay, that's what it means, or it's 1/10, or the decimal point 1/10. Okay. So this is the homework group work for this section, and let me pause for this now, and we'll get started on this in a minute. But I want to show you one thing before that, so just a second. Come on.